measures in a naturalistic environment. You have continuity of data collection so that we are able, as compared to standard clinic visits, we're able to look at within subject trends and not need to compare necessarily to populations that they do when they take standard neuropsych assessments in a clinic. So additionally, this way we can look at variability in any one of these cognitive measures, because that sometimes is more predictive of an issue than the actual score on a cognitive test itself. So this gives clinicians and care managers a real framework for detecting patients' cognitive problems early and giving them early feedback on treatment interventions. So a little more motivation. Why do we need this new kind of model of care? We have a huge aging demographic with concomitant healthcare costs and issues on health disparities. We need scalable, low-cost approaches to getting as much information as we can to help both quality of life and lower costs. And the new opportunities that are growing every day are mobile technologies. Phone interfaces are becoming more and more ubiquitous, both with low-income populations, the typically underserved, as well as aging populations. Additionally, sensor improvements, huge, smaller, cheaper. We wear almost ubiquitously. The phone itself has many sensors embedded in it. Many people are wearing watches with sensors. And additionally, all the advances that have been talked about in big data approaches to analyzing this type of streaming data from the home. So if we think about how we can develop a system to collect all this data, analyze it, putting the user at the center for this type of monitoring, inferring a user model, and then being able to feed back this information to caregivers, family members, clinicians, as well as the individual themselves. We have an opportunity to intervene. Most of our work has been on intervening in the area of cognition. So sleep is an important influence on cognitive behaviors, cognitive performance. Physical exercise is probably the most important type of intervention that you could do for an individual. Stress management, et cetera. But looking at cognition itself, how can we really make a contribution? You'll notice in this list of standard neuropsychological assessments that are typically done in a clinic environment, speed of walking and finger tapping are pure, you would think, pure motor speed tests. But walking in itself is a cognitive issue. You'll notice when you have to think or do a dual task, you typically slow down in walking or observe other people. If you need to balance more in a rough terrain, your speed will slow. Finger tapping test is just how fast can you hit a lever on a test that's done in the clinic. Again, pretty much motor speed. The trail making test is another important one, along with these other types of tests that are typically done by a neuropsychologist. It requires an individual to come into the clinic, take about an hour and go through all of these tests. Mostly it's typically done with paper and pencil for many of the variety of tests on the lower part of the list here. The problem is that it's not naturalistic. People gear up for this type of test. When they're in the clinic, they're working at their top performance and concentration. And additionally, these tests, for the most part, like the trail making test, one of the most predictive ones, can only be given once every 6 months. Typically, it's not given more than once a year. This is very infrequent data that is not necessarily representative when you see a little later what the types of variability in these scores are. So trying to replicate the walking speed test in the clinic, they measure, it's called a get up and go. You get out of a chair, walk 15 feet, back and forth, sit down again, and that is timed. One single measure. Well, in the home, we've been able to, by putting just very, very inexpensive passive infrared sensors on the ceiling or in a hallway and measuring as an individual goes back and forth. And this is for people living alone. We had 200 subjects monitored for more than 4 years, just passively collecting this data to develop some exploratory hypotheses. We were able to collect data and then compare it against cognitive measures and their medical history. So the idea was to measure data from the home in a very simple way. And let's see, we have an example of what the data would look like. This is a plot of distributions on velocity over time of speed of walking through a hallway. And the warm colors, of course, represent the peaks of the distributions. And over time, you can see that the speed for this individual started out about 75 centimeters per second. And at the point where there was a stroke 2 years in, the walking speed decreased and then recovered. But you'll see similar types of patterns occurred earlier without a medical explanation. For another individual, the medical diagnosis of mild cognitive impairment, MCI, occurred at about year 2. And CDR is the clinical dementia rating score of 0.5. That is a very delayed indicator. It takes usually several years to make this diagnosis. Here, looking at the decrease in walking speed, just one indicator, we could have diagnosed the slope, the trend within subject trend, much earlier, within the first year. Now, another way to measure motor speed, and this is looking at the typical finger tap test that is done. Again, I was saying just how fast can you tap your finger and push that lever over a period of usually half a minute. And what we looked at instead was login data from the computer. This is something where people, it's not as subject to cognitive variability or context changes, but people repetitively keyboard in their login data. And we were looking at elderly participants' use of home computers and got a fairly good correlation with the finger tap test, R of 0.77. Again, this is an indirect, quick measure over time, not that many points, but if you were looking at an individual, this is different individuals in this case, within getting their own computer session and comparing that to their yearly test on the finger tap. So if you look at instead within subject trends, you'd be able to even detect, use this type of measure to detect early. Now, another completely unobtrusive type of measure of behavior is the mouse movement. If we passively just keep track of how a user moves the mouse and what the pixel to pixel speed is, we'll typically we see in individuals, and what you see on the right here is a plot of one particular typical subject, where in a computer session, you usually find a bimodal distribution, and you want to remove the slower speeds to the left. And this is just a probability density distribution, where you want to separate active moves from just browsing moves. A lot of times users you'll notice that the mouse movement just corresponds to their attention, where they're focusing on the screen. We want to remove that type of movement and concentrate on the peaks of the active move and measure that for every computer session. And again, that will correspond with the motor speed types of measures that people use in the standard neuropsychological tests. Other opportunities you have, if you're just looking at behaviors completely passively, you can look at linguistic analysis, either in writing or in speaking. We haven't looked at text analyses yet, but with linguistic analysis, very simple measures of complexity of the types of words that are used. An interesting study was done with the author Iris Murdoch, who published a number of novels over the years, was eventually diagnosed with Alzheimer's disease. And all of her novels were very successful. She didn't use editors much. And just by looking at the complexity of the novels that she wrote over time, there was a sharp decline in linguistic complexity. And this is only in retrospect. One of the problems with high-performing individuals being compared to the population norm, if she went in for these tests, it would not be picked up. People that are high functioning, typically highly educated, or have jobs that push their cognitive performance, you're not going to be able to detect problems until the very end. And they will typically, in performance on most of these tests, have a sudden drop off, whereas people with not as high performing will have a gradual decline. So complexity is one area you can use for linguistic analysis. There are other machine learning techniques that have been used to classify writings from people with schizophrenia from healthy normals. And also a couple of different algorithms have been used to diagnose depression early. And that is either word spotting or the general linguistic approach for classification. So a second type of analysis is taking statistics from voice, from the phone. That has been used to diagnose depression early and also to monitor Parkinson's. And finally, simple movement, either the accelerometer on your watch or accelerometer on your phone, GPS on the phone, and sometimes just usage of either email, text, and social connections, phone calls, can give a good indication of socialization, but movement in general can help with bipolar issues, where you want to anticipate when somebody is going into a depressive state or coming out of a depressive state. So there's lots of opportunities for completely unobtrusive monitoring of behaviors to give indication for neuropsychological issues. Now, I wanted to switch from completely passive unobtrusive to measures that we can derive from cognitive computer games that we've designed. We've looked at games that can extract measures of working memory, executive function, divided attention, and verbal fluency. Those are some of the standard measures that neuropsychologists are interested in. So not to actually read this slide, but just to give you a sense of what types of cognitive measures are important, going from visual scan, search, mental rotation, working memory is long-term memory, various types of attention, and then how we can look at aspects and test those. So just to show that we need to develop mappings from the measures that we want to look at to how we can extract them from behaviors. So in our effort to do this and looking at what kinds of games, casual computer games that older adults already enjoy playing, which one of those could we adapt or slightly modify to help us extract some of these measures? On the flip side here is the simple memory or concentration game. Scavenger hunt was used to model the trail making test. And the trail making test is one where on paper and pencil, you search and link from 1 to 2, 3, 4 for first part of the test. And then in the second part of the test, you would have to do set switching and go from 1A, 2B, 3C. And the simple timing of that was the score that you would get. In a game format, we're able to modify this and put different types of target information in the top. The 21 tally game, the brown one in the center, is a divided attention game where we look at people's ability to play blackjack in rows and columns at the same time. And then we had a couple of verbal fluency games, just word searches. Now for the very simple concentration game, it's clearly a game that can measure memory. And our goal here was to see if we could get a single metric from a performance as they play a game to look at, with repeated play, a single measure of the memory buffer length. So as patients would, or participants here, would flip over a card and looking back, how many steps would they have had to remember it to be accurate? And then looking at mistakes that are made, all the while correcting for chance, we can come up with memory capacity as the intervening number of events, the intervening time, and the memory load required to then model it with a Weibull distribution and get a, looking at the curve, be able to, with a single metric, characterize the memory capacity. And this is work by Misha Pavel. In our game designed specifically to extract a measure of divided attention, we looked, as I was saying before, at an individual's ability to play blackjack successfully and looking at rows and columns at the same time. And here we found that it really didn't matter how well they could play blackjack or their math ability, but rather we're looking at the success, the relative success. Was it equal on rows and columns? And then have a measure of their daily divided attention. And then we would use this as an example here in coaching and trying to improve divided attention. Now, the most successful game that we had in having the closest correspondent with a particular neuropsychological test was the scavenger hunt, where we would have strings of varying complexity posted in the white bar. And the goal for the user was as quickly as possible to find that string and click in order, B2, A1. Now you'll notice there were distractors here, and some strings like 1, 2, 3, 4 would be the most, the simplest and the least complex, and nonsense strings would require a lot more memory and more cognitive complexity, so that our analysis would be with repeated strings and repeated play and trying to make it fun and challenging. We had lots of prizes and feedback. We were able to separate out the time for recall, just to recall the next target, the time to search for a target, which would depend on the number of ideal targets as well as the number of distractors, and then the simple movement from one target to the next. So very complex strings would be heavy on the recall. Lots of distractors would be heavy on the search, and move would be for the very simple 1, 2, 3, 4 types of strings. The results that we were able to get comparing comparing our modeled trail making score from the game performance over time to the measured score in a neuropsychological assessment, the open circles here at the bottom are where subjects performed more quickly because they were just doing trails, what's called trails A, the 1, 2, 3, 4, 5 on paper. Whereas trails B was the set switching, which took longer, but the correspondence that is shown here with an R² of 0.78 is very comparable to what's seen in standard test reliability for trail making. So this type of, if you can get older adults or anyone to be able to, in neuro rehab, to be able to play this game frequently, you can do just as well as a standard trail making tests in being able to monitor them. We also use data from the watch device and heart rate to look at ectodermal activity, which is sweat that relates to stress, and being able to feedback from electrodermal heart rate and heart rate variability, feedback information to individuals and classifying their stress in real time. So this is moving from pure behaviors to somewhat physiological. But again, if we look at the health coaching approach, we can be using this cognitive information to do early detection of medication interactions. We can feedback early information to caregivers and clinicians about cognitive problems as they occur, and maybe instigate, use this as screening to follow up with a more formal assessment, but also be able to show rehab results and make this part of coaching to give immediate feedback. So in our laboratory, let me skip one slide. In our laboratory, we're able to offer a variety of types of interventions: interactive video exercise, robotic interventions for socialization, as well as other networking for socialization, sleep management, etc., all relating to cognition. Another important aspect is to be able to communicate with family members, bring them in as part of the care team, as well as feeding back information to clinicians. So just to summarize, the expressed behaviors that are routine and in a naturalistic environment hold a lot of information about an individual's cognitive abilities and even different specific aspects of cognition. And the idea of monitoring in the home environment with these repeated frequent measures allows us to have within subject trends that gives earlier detection and more reliable detection than trying to compare results on an infrequent measure in a clinic to a population. The final point, this is a very inexpensive and scalable approach. And just wanted to thank members of our lab that have contributed to this and can take time for questions. Thank you.
Thank you, Dr. Jimison. That was really wonderful. So I don't see questions in the chat. If you have a question, you can raise your hand. Maybe I'll get started. I do have a question for you. So what I think is really interesting is an application to optimize neuromodulation therapies using at-home monitoring. So for example, to treat chronic pain, you can use, you might have a spinal cord stimulation implant in you. And, some people feel relief, some people don't. Nobody really understands how to optimize those parameters. A lot of times patients get explanted because that doesn't work for them. And I know companies like Medtronic and Abbott and people who manufacture those stimulators are very interested to think about at-home monitoring and how can they use the behaviors to feed back to, say, the clinician and to better understand how to titrate the stimulation parameters. Have you thought about these types of applications or worked with, and same with Parkinson's disease and deep brain stimulation? So just thinking about optimizing therapy.
Right. I think, for the applications that you mentioned, I think the stress monitoring is something new that is really very appropriate. It's difficult to measure with simple wearables like, these watches. Some have embedded electrodermal activity that is one indicator of stress, and almost all will have the heart rate, but to get heart rate variability requires very, very clean data. And you need to use the accelerometer to be able to clean that data, understand when the sweat may be due to movement and exercise as opposed to anxiety and emotional arousal. It's a little noisy and challenging at this point. If you're able to wear ECG leads, and it's a short-term issue, then you can get very reliable signals for heart rate variability and use that as your primary indicator. But in our case, with older adults, the skin is very thin, fragile. People can't wear these pads that stick to the chest for more than 3 days. So if you have a short-term type of intervention, that high quality data can be very good, or wearing the band, like some of these exercise bands. But generally, many applications, you want to minimize the additional work that an individual patient needs to do. So even charging these devices becomes a burden and people stop the intervention. The adherence falls off.
Mm-hmm.
It's a real challenge, but you know, a lot of this is very task dependent. Do you have a short-term kind of monitoring that you want to do, or is it a lifestyle of monitoring? Very, very different kinds of approaches that you might want to take.
Sure. I see you, Paul. I'm just going to ask one question from the chat and then I'll hand it right to you, Paul. So we have a question that says, are continuous PPG measurements useful in the classification of these diseases in combination with the continuous non-invasive measurements presented at the beginning?
Oh yeah, that's what, and I think certainly PPG giving you heart rate, perhaps high quality heart rate variability. And what we do in getting heart rate variability for stress management is really critical. And if you're willing to throw out movement that is just making the data way too noisy and monitor when you do have those clean periods as defined by the accelerometer, it can be very, very helpful. And any aspect of if you're trying to look at AFib, atrial fibrillation, for example, then it's a really, it's not as challenging to detect that. And even Apple Watch attempts to do that currently.
Great. Paul?
Can I make a follow-up question? Sorry, to the chat question.
Sorry, Hector. Sure, go ahead.
Yeah. And what kind of states can a PPG measurement give you besides arrhythmia? Or is arrhythmia the main kind of indication that it's giving you?
Well, arrhythmia is great for cardiac, you know, as a cardiac diagnosis. You can't get from a watch or, you know, PPG, you're not going to do sophisticated ECG analyses. You will, and so AFib is about it. What I was trying to get at is this heart rate variability being a very, very important indicator of, you can look at stress recovery at night. Athletes are using this right now in order to decide how to train the next day for general stress recovery. But for right now, stress is really under-recognized as an important indicator of health risk, that it affects all of our organs and basically all diseases, makes both quality of life and length of life issues really important. So using PPG for heart rate variability can be really critical and a very important indicator, but requires a lot of cleaning and analysis. And I think that's some future work.
Thanks, Alden. Really appreciate it.
Thank you. Paul?
Hey, Holly, great talk. One of the things I think that's really exciting, at least from my perspective, is, you know, using these behaviors and being able to track and monitor them closed loop, right, to have just-in-time interventions. And so I wonder, have you or anyone else in this field yet like closed the loop for a particular application and kind of showed that, you know, if you provide that intervention just in time, as it can be predicted when it should be provided from the behavior, that improves wellness or, you know, has some effect? Or is most of the work still kind of open loop?
No, this is the whole approach with health coaching is for just-in-time feedback that does close the loop. So for example, if you're doing sleep monitoring and they've made some behavior changes to improve their sleep, you want to give them immediate feedback on, yes, it worked, and let's continue this particular approach, or feedback on exercise, their cognitive performance. They can look to see if they're improving with memory or divided attention. But yeah, your point is so important, because the things that are known and have been shown in studies is that tailoring to individuals with immediate feedback that is, you know, is their feedback, not just general education, improves the health outcomes. And so just-in-time feedback, which we've been trying to do with stress management, we've done with sleep and exercise, and cognitive performance. There have been a variety of studies that show closing the loop using health coaching techniques does improve outcomes.
Maybe I can just follow up with one thing. So in terms of also closing the loop, I guess that, one parameter or is exactly what window in which you consider just in time, right? So I guess like in the sleep case, you're not waking somebody up, you're telling them when they wake up, right? First. And so how much research, or like when you think about optimizing the intervention, how much is known about how to do that, and how much has to be done just purely empirically? And
yeah, no, that's a good question. It is very task dependent. Smoking is one area that has been heavily studied where just in time is critical. You want to catch them. So for health coaching, we do motivational interviewing. We need to know their motivations, why they want to change, their barriers to change. But for smoking, for example, or even weight loss, triggers, what's going to trigger them? So GPS, knowing when they're, for weight loss, when they're near Dunkin' Donuts or the, whatever their trigger might be, is when you quickly intervene, perhaps with a buddy, a call from a buddy. For smoking, you need to catch them at their triggers to be effective. Whereas, yeah, sleep, getting them the next morning is more appropriate. And exercise, not as critical unless they've made a goal to exercise at a particular time and you can intervene. So it's very task dependent.
great, thanks.
Great. So I don't see any questions in the chat. If I may just ask one more question while others might be thinking of typing. So you mentioned variability in the very beginning, right? So, a lot of these tasks and performance, motivation, attention depend on the time of day, whether they slept well or not. Have you thought about and explored all of these factors?
Yes.
And when you look at correlations of performance metrics to sort of traditional tasks?
Yeah, that's been fascinating because when we've analyzed time of day, it tapers off. People fatigue in time of day. And this is for older adults where it's going to be more observable. And just to link back to the standard neuropsychological tests that either go on for an hour or an hour and a half, people fatigue and you get much worse results at the end. And there's so many problems with what we're calling our supposed gold standard there, that even clinic visits are not reliable and introduce a lot more variability that way. But yes, there are definitely fatigue effects for time of day. But the interesting thing about people with cognitive problems and the dementias is that they are lucid some of the time and then regress. So being able to monitor that either by walking speed or how they interact with the computer in a computer game, we've seen, I'm thinking back where we saw the most striking difference was with executive function on a free cell, which is a solitaire game requiring a lot of planning. And we found that variability in their scores was even more predictive than their actual performance. And by scores, I mean our way of scoring was comparing motion, how quickly they were moving towards solution, not just a score in the standard game.
If we have a follow-up, kind of a related question is, can you detect the difference between fatigue and boredom?
Well, that's a good question. There's a lot of confounders. When I should have emphasized this, because whenever you're measuring behaviors, there's context differences. And no, you can't except that within a particular person, the motivations are likely to be more continuous than going from person to comparing different people. And the boredom effect can be averaged out within a person typically, but perhaps, yeah, boredom would happen over time. And I guess, one way to look at it, these are all very indirect measures, but they're free. The challenge is trying to, like we were doing with the mouse movements, how do you extract the meaningful part out of a lot of data that you're collecting? And if you can remove the boredom aspect, that would be really, really challenging, but helpful.
Mm-hmm. So we have another question in the chat. How is the health coaching implemented practically as a business, which I think you probably have some insight here, if it is a long-term monitoring in terms of patients investing money?
Oh, I'm not a great one to talk to about business. In this case, we had a project manager who was very natural and a software designer that wanted to start the business. One of the mentors, and we had at Northeastern University, and I'm sure this is true other places, ICOR is an NSF sponsored initiative to help people take ideas, bring it to business. So the project manager and software developer did that. I wouldn't say it's been successful. One problem with home health interventions is who pays for it, who's buying it. If it's for older adults, is it the adult children that want their parents to have it? Do insurers think it's worth it? What's happened with a lot of disease management companies that try to target the high utilizers in medical care costs is that the purchasers expect, the medical centers expect it's going to save them money, and out of whose budget? And it's been very hard for small businesses to break into this area. It's much easier, we started working with Sweden and Finland, where the healthcare is more holistic. Anything that helps holistically, doesn't matter, the budget is global from the county. So it's easier to have a business model for this type of care in countries that I would say have a more logical kind of approach to financing their healthcare.
Okay. I don't see any more questions on the chat. I'm going to just open the floor in case anybody has a question. You're welcome to unmute and ask now. Okay. All right. Well, we'll have a chance at the end, hopefully. So I'll pass it back to you, Metin.
Yeah, we will have a break and we will come back. Depends on where you are. I think it's the 17 minutes. Good. Okay. So 1:50 with the California time, and we will have a couple minutes break. And see you soon at the plenary talk by Paul Sajda. Okay. Thank you. Okay. How are you doing, Paul?
Excellent, sir. How are you?
Wonderful. Good to see you.
I see that some schools are closing a little early, right? Because Princeton just shut down for the semester because of COVID. So Cornell was yesterday.
Yeah, they completely closed. How is Colombia?
We just got to know we're still good. I mean, we're still significantly below 1% in terms of COVID rates at the moment. So we're okay.
Okay. I think this winter will be difficult, but I believe that it's by spring.
Yeah,
We'll
I
be
think
much
so
better
too.
shape.
It better be, because else every winter we're going to say the same thing for the next spring. So
Are you in the office or are you at home?
no, I'm at home today. Yeah.
Okay. Okay, we have 1 more minute to go. Did you check your slides?
Yeah, I'm ready to go whenever I can share whenever you guys are ready.
Okay.
I see you, Misha.
Really?
Get your head in.
I met. Too bad we're not in Capri doing this, or actually even San Diego, right?
Very soon, Misha.
Very
Trust
soon.
me. Just wait for the. I'm saving a lot of lime milk for you, Misha. Lion's milk.
Yeah.
I think he got the message. I can see the big smile on his face. Okay, it's 1:50 p.m. in California. Wonderful to see you back again. It's a great honor and pleasure to introduce my distinguished colleagues, friends, Dr. Paul Sajda. He's currently the endowed professor, Vikram Pandit Professor of Biomedical Engineering and the Professor of Electrical Engineering, as well as the Radiology at Columbia University. He's also the member of Columbia's Data Science Institute, affiliated with the Zuckerman Institute of Mind-Brain Behavior. I will not tell the years, but he received his BS from MIT, Master and PhD from UPenn, and his research focuses on what happens in our brain when we need to make a urgent decision, and also what processes and representation in our brains drive our understanding, underlying preference and choices, especially when we are under time pressure as usual. And his work in understanding the basic principles of rapid decision-making in the human brain relies on measuring human subject behavior simultaneously with cognitive and the psychological states. He has developed novel systems. Actually, he is collecting the data or measuring the human subject behavior with to uncover the construct real-time brain-computer interfaces that are aimed to improving interaction between the humans and the machines. He has applied these platforms to understand how deficits in rapid decision-making may underline and be diagnostic of many types of the psychiatric diseases and also mental illnesses. He's a founder of several neurotech companies and works very closely with diverse group of scientists and engineers, including neuroscientists, psychologists, computer scientists, as well as the clinicians. He's a fellow of the several the institutes, including IEEE, EMB, SSS. He's currently the chair of the IEEE Brain Initiative, and also he's the president-elect of the largest, oldest biomedical engineering society in the world, IEEE Engineering in Medicine and Biology Society. We are delighted to have you here, Paul. You have the floor.
Thank you very much, Metin. And I just wanted to, once again, thank the organizers, especially Gert, for putting this together, and all of the sponsors. I think this is just really a wonderful workshop and conference. And what I want to talk about today actually kind of overlaps a little bit with the previous mini symposium and this symposium, in that I want to tell you a little bit about systems we've been developing and evaluating clinically for closed loop, non-invasive neurotherapeutics. And so, I think one of the great things about this workshop was really, making it clear that one needs to consider the brain and the body, right? And when we think about BCI, we can actually put that in quotes, right? In the sense that there are lots of different ways to measure the state of the brain. And not everything has to be an electrode in the brain or on the scalp, right? There's not just, what's happening in the central nervous system, but the peripheral nervous system. There's, as Holly was talking about, behavior and ways in which we can infer that through what's happening overtly via our musculoskeletal system, what's happening in the environment. And the key, I think a lot of us believe, is how those measurements will enable us to close the loop, and closing the loop in a way that that allows us to provide an intervention that can, mitigate symptoms or improve performance. And this closing the loop is a non-trivial thing. Shree's on one of the folks who's leading this mini symposium. She's a control theorist, and as soon as you put a feedback loop in, there's lots of considerations one has to deal with. Nonetheless, there's this hope that closing the loop and actually having two controllers in this loop, one being a machine or decoding models, the other being our brain, that one, they can converge to kind of solutions to particular problems that help us as individuals and so forth. And so, there are different types of closed BCI systems. On the lower right, there's this idea of using kind of closed loop to either augment performance or improve interaction of humans and machines, right? So there's this kind of like a technology focused consumer performance optimization approach. And then on the other side, there's clearly, these medical applications. And I think we've talked about already that if we look at, for instance, the utility of using deep brain stimulation, and with that deep brain stimulation, instead of having that stimulation on, constantly, to actually deliver the stimulation based on the endogenous brain states of the individual. And there's a lot of different types of rationale for that, everything from kind of engineering and hardware issues in terms of conserving battery power and so forth, but also the belief that our brain is highly dynamic, right? And so when we're hitting it with some intervention, the context in which our brain is at that moment in time, our brain state, will likely have a role to play in terms of how that stimulation affects us, whether it changes our brain through plasticity, whether it encodes memories, whether it actually causes some problem or deficit. So this idea of closing the loop enables us potentially to provide more precise stimulation and more personalized stimulation, because obviously our brains are doing very different things at very different times. My guess is that, on the West Coast and the East Coast, our brains are in different modes just based on the time of day it is. So, so I want to talk a little bit about how we can look at using closed loop BCI type systems particularly in addressing questions and issues in mental health, right? So probably not surprising to anybody, but mental health disorders are really the most costly health issue in the United States. In fact, some people are surprised to see that it's even more costly in terms of overall economic, social costs than cardiovascular disease. Things like depression is really the leading cause worldwide of disability, right? So it's a huge issue in terms of a global burden of disease. And, back, as many of you probably remember, when President Obama launched the Brain Initiative, it's already, 8 years ago or so. One of the real rationales for this, right, was to try to do the science, both the basic science and the clinical science needed to improve and help mitigate mental health disorders. And I think that if you take a critical look at the Brain Initiative, there's been some amazing science that's happened, basic science, and also some translational science. But what has been impactful yet in terms of improving, mental health of human beings, of us, it's still, somewhat unclear where we are, or we clearly have, let's say, a long way to go. And part of the reason for that, at least if we think of mental health disorders, is that, causes of neurological and psychiatric conditions really remain largely unknown. And that's due to the fact that the human brain is very complex. And in fact, not only is the human brain complex, but, if we try to do work in animal models, it's not always clear that those can that work can translate into work that has applications to, let's say, looking at mental disorders in humans. So, what I want to focus on is particularly non-invasive therapeutics that utilize closed loop architectures and specifically look at the issue of depression. And so some of you might know that there's a number of ways that an individual can be treated for depression. Everything from cognitive behavioral therapy to pharmaceuticals, but there's also neurostimulation techniques that are approved by the FDA, and one of these techniques is called transcranial magnetic stimulation. So transcranial magnetic stimulation, this is a non-invasive neurostimulation technique. So this is not something you have to have neurosurgery for or implant something in the brain, but it's essentially a treatment in which one goes, let's say, daily for a period of a number of weeks, gets treated by a physician, a psychiatrist. And the idea behind treating with neurostimulation is that in cases where cognitive behavioral therapy or pharmaceuticals don't work in treatment-resistant depression, as it's called, there's been evidence that this neurostimulation actually works, right? It improves the symptoms, it enables remission, and in many cases, really long-term effects that dramatically improve the quality of life of the individuals that are affected. And so, so this little machine here, what this thing is actually it's a coil. It's like a figure-8 coil that that uses a magnet or generates a magnetic field that can excite the brain. So essentially, it can drive electrical activity in the brain through electromagnetic coupling. And this little picture here, and this is from actually a company that sells these instruments. So one positions this, let's say, spatially over the head, and oftentimes it's put over prefrontal cortex and a part of prefrontal cortex called dorsolateral prefrontal cortex. And then there's a dosage, and this is a trigger. And what this company is showing here is what looks like this electromagnetic radiation getting into the deep parts of the brain. Now, this is a little bit misleading in that if you understand, the physics of TMS, it turns out TMS itself only excites cortical tissue relatively superficially. So the depth penetration of TMS is only like perhaps a centimeter or so. So if you have a a target, a therapeutic target that deep in the brain, actually this TMS is not going to affect it, at least directly. And so, this has been known for, for a while. And in fact, as one looks at the success rate of TMS versus other non-invasive neurostimulation methods used to treat depression, like electroconvulsive therapy, which actually uses very high voltages and is known to activate tissue deep in the brain, though it has a lot more severe side effects, that the range of the remission rate in blinded trial is much lower than you have in ECT, right? And so why is that, right? So is there a rationale or a reason that this could be the case? Well, if we go to the what's happening in deep brain stimulation, we know that the therapeutic target in many cases is actually deep. So a electrode is implanted in part of the anterior cingulate. So it could be the rostral cingulate or subgenual cingulate, but that's deep, right? And so if invasively the target is deep, then why is, the TMS might not be optimized to hit these deep targets. And therefore that could be one reason that that the treatment is not as effective as ECT. Now it's known, for instance, that this dorsolateral prefrontal cortex, where the TMS we know can activate, is connected through structural and functional connections to these deeper areas that are the therapeutic target, right? So the hypothesis has been, well, maybe you can indirectly drive these subcortical areas, but perhaps there's something more complicated going on, and sometimes you drive them and sometimes you don't, right? And so what we kind of looked to do was take a look at this in a little bit more detail. And this, is kind of maps out the brain, and here's our figure 8 coil again. And once again, over prefrontal cortex, this area that is going to be stimulated by TMS. And so there are all these different projections to these different areas that are clearly important in treating, mental illness and everything from depression to obsessive compulsive disorder. I want to just focus on this little yellow area here, which is this deeper area that includes the anterior cingulate and the subgenual cingulate. And so one hypothesis is that we know there are these structural connections, right, between this superficial area and these deep areas. But what's also believed is that there's, dynamic functional connectivity between these areas. And one hypothesis is that what indexes this functional connectivity are these oscillations that we see in the brain. And so one of the strongest oscillations in the brain is the alpha oscillation. This is an oscillation from 8 to 12 hertz. We see it very strongly in occipital regions of the brain, the back of the head, but it's also in prefrontal regions. And so, if I won't say that it gates, but I'll just say, let's say it's an index. So if we look at oscillations, right, and in particular, look at the phase of the oscillation relative to, let's say, the coupling between these two different areas, one hypothesis is that at a given phase of this alpha oscillation, these two regions are coupled, but not very strongly, right? But at another phase, there's a much stronger coupling. Right. And so if we believe that, well, one of the issues or with TMS in terms of its efficacy is due to the fact that, well, we're not actually hitting DLPFC at a time where it's strongly coupled to the anterior cingulate, then we might really not be driving it that strongly, right? So, so maybe what we want to do is we want to measure in real time what the EEG activity is, so the oscillations here that we would measure from EEG, and then determine at what phase we should apply the TMS to, let's say, maximally engage these deep areas. So we have our TMS target, which is the superficial, and we have our therapeutic target. And we're going to look at brain state, dynamic brain states in terms of these phases of these oscillations to try to optimize the activation of these deep regions. And so that's the hypothesis we wanted to test. Now, to do this required a huge effort that included also building a new kind of instrument. And so I first want to call out, my students, Zhao Zhao's son, as well as Joseph Fowler and James McIntosh. Zhao Zhao presented a poster on some of this earlier today. And so this was an effort both at Columbia, MUSC, Mark George's group, and Truman Brown, as well as University of Wisconsin, where we created a simultaneous fMRI, EEG, TMS system, and we just call it FET for short. And the rationale for that is, if we look at what we're trying to do here, is we need EEG to track these oscillations and the phase of these oscillations. We obviously need TMS to, in fact, to actually deliver the neurostimulation. And we need fMRI to look deep in the brain, particularly at the bold response deep in the brain, to just show that we're preferentially engaging the target as a function of the phase that the TMS is applied. So I'm not going to go into all of the issues that we had in terms of building this thing, but just if you remember your basic magnetism, that we've got a really big magnet here that also has a changing magnetic field due to these gradients. We've got like a cap with a bunch of wires. We've got actually active high dB/dt TMS system. So all these things, they don't really like to work with one another. So we had to build a combination of hardware and software to deal with interferences, electromagnetic interferences, both between the instruments as well as how these different types of magnetic fields might introduce physiological artifacts in one modality or the other. But if you just believe me for the moment that we actually got this to work, we can first kind of just take a look and say, well, if we apply TMS over DLPFC, and do we actually engage the anterior cingulate, right? So independent of whatever phase we're applying. And of course, there was some evidence of this before, but we needed to validate this, and we wanted to validate it within the context of an integrated instrument. So this is kind of a group level result where this red region is actually a mask, or it shows like an atlas of the anterior cingulate. The green shows the region that is significantly, or those voxels that are significantly activated by a TMS pulse. And this is then what's called, the evoked hemodynamic response, which shows that at the, if this is the time of the TMS pulse, this is the activity that you see. And you see kind of the classic sluggish bold response, but it's clear that activation of DLPFC does affect the therapeutic target. So now the question is, all right, if that's true, what happens if we look at the phase of the EEG, the prefrontal EEG, relative to the TMS pulse, right? And so these are results for 4 different subjects, and this is essentially the normalized bold response. Okay, so you can just think of it as, in this previous picture, it's kind of like the amplitude, normalized amplitude of the evoked response, as a function of the phase of the EEG at which the TMS is applied. So if you look at this individual, right, you see there's a very big effect when that TMS is applied at minus pi over 4 radian phase compared to plus pi over 4. It's actually almost an 8-fold increase in the strength of the evoked response. What's also interesting to note is that there's variability, right, between subjects. So this subject actually has kind of the opposite effect. The preferred phase for this individual, in terms of maximally engaging this deep therapeutic target, is at plus pi over 4. Right? So, we do this simultaneous measurement and stimulation in the scanner. And this is all done open loop, right? So what we can do is we can kind of randomly apply the TMS and then look retrospectively to look at engagement of the anterior cingulate and its subregions as a function of the TMS timing relative to the EEG phase. But we wanted to go further, and we wanted to eventually use this information to close the loop. So first, I want to show these are some results where we had, and I believe this is for 14 healthy individuals. So this is just healthy individuals, and we looked at, so here, this is our little atlas, which now takes this anterior cingulate and divides it up into regions. So this is the dorsal anterior cingulate, the rostral anterior cingulate, and this subgenual cingulate. And each of these has been implicated in different ways in terms of how they are potentially related to networks involved in depression. So in our healthy control, our group, we actually see a strong phase effect. So anything that's hatched here means that there's a effect of phase on the activations in this area in terms of the oscillation phase relative to when TMS is applied here. We wanted to then look at a patient group. So we then started a clinical trial, a relatively small clinical trial, where we then took a set of patients that were diagnosed with major treatment-resistant major depressive disorder. And when we look here, the major effect we see is only in this rostral part of the anterior cingulate. And I'll come back to that in a little bit. But what we could do in both of these cases was identify a preferred phase for each individual. And then we could come up with a paradigm where we said, well, if we know what their preferred phase is in this open loop case, we could close the loop. Now, we can't close the loop, at least in terms of looking at a treatment regime for healthy controls. Because what's approved for FDA treatment of depression requires repetitive TMS of about 20 minutes to half an hour a day over a 30-day period. So healthy controls can't go through that. But we can do is do a study where now we're using the information from this, EEG, fMRI, TMS system to now close the loop. So I'm jumping ahead of myself. One other thing I wanted to mention before I get to the closed loop piece is that we can also look a little bit at why there might be this phase dependent effect. So in addition to looking at just whether the TMS preferentially activates a region, right? So the TMS at this DLPFC activates the deep regions. We can also look at whether there's some kind of coupling of the phase to the functional connectivity between the DLPFC and this subgenual cingulate. So this is known to be kind of an important connection. This is those of you that know Helen Mayberg and has done a lot of work with deep brain stimulation. In many cases, the implant of the deep brain stimulation is right here at the subgenual cingulate. So one reason that there could be this effect might be that this connection itself is phase dependent. And so we can look at that both in the patient group as well as the control group. And lo and behold, we do see that. These are as a function of different phases, what the strength of that connection is. And we do see that there's an effect on the actual functional connection between the TMS target and the therapeutic target. And at least in terms of the subgenual cingulate, because we know the subgenual cingulate then connects to all these other regions, that might actually be why we're seeing even a broader effect in terms of activation of the ACC as a function of phase. We can also, before I jump to the closed loop, we can even do some causal modeling. So one of the, I think the really cool things about now, if we can image both high spatial resolution, high temporal resolution using the EEG fMRI, as well as perturbation through TMS, now we have ways in which we can look more closely at causal relationships. And just two things I wanted to point out here. One that we thought was really interesting. So this is all a data-driven, what's called a dynamic causal model. Essentially is a Bayesian model to look at directional interactions. And so here we're looking at interactions between that dorsolateral prefrontal cortex and this subgenual cingulate. So essentially this connection, right, between this yellow area and this blue area. Here, this is just a correlation, right? So there's no direction here. But here we try to actually learn if there's directional effect. So the first thing that's interesting, if you just learn, take that model and the data, is that you just look at the arrows and the color of the arrows. And what was, I think, really cool and not surprising to us, but it was, I think, validation of what we think is going on in the brain of an individual with MDD is in the healthy controls, we see this an excitatory projection from the DLPFC to the subgenual cingulate, and then an inhibitory connection back up. So this kind of feedback loop that includes excitation and inhibition. And this is like kind of very robust to, which model and how the models are chosen. In the MDD group, we only see excitatory connection. So there's no inhibitory connection in this feedback loop. And why is that important? Well, one hypothesis about, why, first of all, what are some of the issues with major depressive disorder and why we might want to use neurostimulation to combat it has to do with the subgenual cingulate and the cingulate regions being overexcited, right? So the excitability is really high. And so you could imagine that if there's no, no inhibitory element in this feedback loop, this is going to be an overexcited loop, right? So that's one thing to look at. And so this is these two groups before any treatment or anything like that. So there's clearly a difference in the network architecture that is, we infer from the neuroimaging, but also where this neurostimulation effects happen. So we see in this healthy control group, we get strong effects that look like it's modulating this connectivity, right? So this stars here means that there's not just a neuromodulation, but there's a phase dependence of that neuromodulation or stimulation. And we don't actually see it on the MDD group before treatment. We do see, so it's not on, we don't see it on these connections. We do see an effect that that is directly on the activity of the subgenual cingulate. I'll mention this later on because once now we go through a regime of treatment, closed loop treatment, we expect this to change at the end of the treatment. So this then gets to the closed loop piece. So what do we do? So now we say we're going to create a closed loop EEG system. And this doesn't require, this fMRI piece doesn't have to be in this loop, and it actually wasn't for this current clinical trial. So this is a double-blind clinical trial that's being run at MUSC. And the idea is that a subject gets enrolled, they get this fMRI, EEG, TMS imaging, where we determine their preferred phase in terms of how the phase at which the anterior cingulate is maximally engaged. And then they go into one of two arms of the trial. They either go into the synchronized arm or the non-synced arm. And so they don't know which arm they go into, the experimenter, or actually the clinician does not know. And they go through a 6-week treatment of half an hour treatment per day. And what we do is so here's the TMS coil and the EEG on. And so we monitor and track the EEG. We then try to recover the online, so causally, the phase of the alpha rhythm. And in particular, we look at their individualized alpha frequency. So we learn that also from in the scanner. And we do modeling to basically create predictions on when to fire the TMS so that we hit at the preferred phase, right? And so there's a lot of signal processing and hardware going on here, and so I'm not going to go into too much of the details. This kind of just gives a little cartoon of what's actually, it's real data, so I guess it's not a cartoon, but in the scan mode, what's happening is we're looking and detecting alpha, prefrontal alpha. Once we have enough power in the prefrontal alpha, we track and fit a model. We make in terms of what we think the phase relationship is. We then make a prediction to see if our prediction is good enough on that model. And if it is, we use it to then generate a TMS trigger, right? And all of this is happening really fast. So like on the order of 100 to 150 milliseconds. And it has to be that fast also because, as you might see here, the coherence time of alpha is not that long. And it's simply, it's a challenging signal processing problem because of the non-stationarity. But anyway, so this is still a double-blind trial, but I want to show a couple of results and then some early results of the clinical outcome in a couple slides ahead. But one of the things that we were interested in is to see if by delivering the TMS in sync with the preferred alpha of the individual, preferred alpha phase, that we could induce entrainment. And the reason for that is in the literature, there's this entrainment hypothesis that says that if you can entrain oscillations in the cerebral cortex, this basically is a possible mechanism for ameliorating the depressive symptoms. And there is this hypothesis that this could be key to increasing the efficiency and efficacy of our TMS. So we looked at that, and the way we did this was, so individuals, like I said, these are all with treatment resistant depression, where obviously as we're triggering and applying the TMS, we're measuring the EEG. And just to give you a little bit more idea and detail of how this works, so patient comes in, they get about 5 minutes of just resting state EEG, and then the closed loop is activated. And then the treatment are RTMS pulses. So they get these pulse trains, and they can get only a certain number of pulse trains. So we do a lot of balancing to make sure the amount of TMS that's delivered is the same in both arms of the trial, that the time is not too much different in terms of the two arms of the trial. But what we can do is we can look at what the alpha phase is after the RTMS is applied in terms of a pulse train and before. And over a session, so let's say over a half-hour session, we can use what's called the intertrial phase coherence, which basically just looks at the relative phase before and after applying the pulse, looks at those across all the trials, and we will then get essentially a vector that says, well, in this case, there's not a lot of coherence, so this vector is not very long, or there's a lot of coherence, right? So then the vector is very long. So essentially all these the pre and post trials are really entrained. And so when we look as for, let's say, two different subjects, one thing that we found that we thought was pretty exciting is the fact that if you look across days, right? So this is 30 different days. These are actually, there's weeks in here, right? So there's weekends. And for a typical sync subject, you get an intertrial phase coherence that increases over time, right? Versus somebody in the unsync group who's getting, TMS at the same frequency. Everything is exactly the same, except the phase in which this TMS is triggered is random. It's not the preferred phase that we identify in the fMRI EEG TMS system. And so there's no change in entrainment for the unsync, or at least in this individual, but there's a significant change, and it's building over days, right? So this has to be a neuroplastic effect that's happening. It's not like, they have this and then it goes down the next day and it, kind of builds up again. And so it's not a transient thing or a session dependent thing. It actually is a neuroplastic effect. And if we further look at this in terms of, whoops, sorry, just jumped ahead here. Hold on, I think I'm having some problems. My PowerPoint. Okay, sorry. If we look across the brain across different areas, right, and we look at these effects as a function of, so these blue curves, so what we're looking at is the entrainment on the first day versus, so the first day of to the 30th day. So the beginning of the treatment to the end of the treatment in terms of 5 weeks, we're seeing strong and significant effects that show entrainment for the synchronized group, but not the unsynced group. And those effects are not only over the target region, so the TMS target, but they're also over, for instance, regions that include the medial frontal cortex, right? So this is kind of regions that would, if you were an EEG person and looking for activation in the anterior cingulate, you would look at these electrodes. So there are effects that are even distal to the treatment, the TMS application. There's also even effects in the occipital region, which we have some theory based on network type effects. But anyway, so these are kind of intermediate results. Zhao presented a poster earlier of some other results that had to do with power changes. But how is this going to have any clinical effect, right? And so, like I said, we're still blinded. And so what I can do is I can show results without breaking the blind by just looking at this overall study and the 2 different groups. But I don't know, and we don't know yet which group is the sync group and which is not the sync group. So first of all, the overall study. So what I'm plotting here is, this is what's called, the Hamilton score, the depression score, right? So this is this clinical score used to assess the severity of depression. And so for this group in our study, they started out with a Hamilton score up here, close to average of 30. And afterwards, so if they completed, they're down here, that's closer to, 12 or so. So them going through the TMS, clearly TMS is having an effect, right? And I should say that the way we're applying TMS is also a little bit non-standard. So TMS applied for treatment-resistant depression is indicated by applying a 10 Hertz rTMS pulse sequence. What we do a little bit differently is we actually apply not at 10 Hertz, but at the frequency of the individual alpha frequency of that person. And so there's a couple of reasons we did that. So one is that if you were the clinician or the RA actually doing the experiment, you could tell whether or not one was in, let's say, one group or the other, if you had the control group always got 10 Hertz, right? If they always got 10 Hertz versus we had personalized IAF for the treatment group, because the treatment group goes between 8 and 12 Hertz or so, you could even hear it in terms of the clicking, right, of the scanner. So so that's really one of the key reasons why we actually had everything the same except the phase triggering. And we think just by, and some of our results, if we look at the efficacy that we're seeing here relative to what's reported in the literature, even just having the rTMS be at the individual alpha frequency, independent of phase, is actually going to be better than the standard of care right now. So that's one thing. The second thing is, all right, so let's look at the 2 different groups. Once again, we don't know which is sync and which is unsync. But what we do see is that if we look at how this Hamilton score changes, and we look at what's considered clinically significant for being a remitter, so being in remission, that in group, typically you have a Hamilton score that's equal to or under 10. We see that group B has, twice as many remitters as group A. Once again, I don't know if group B is sync or unsync, but there's a pretty significant effect. These are still small numbers, but remember, these are data collected over a period of 30 days, also during COVID, right? So this was one of our challenges, is to keep this clinical trial going during COVID. We can also just look at the percent decrease of in the Hamilton score, which is also another measure of the effectiveness of the treatment. And here we also see that group B has about a 10% better decrease than group A. So we're clearly seeing that the TMS treatment is having an effect in terms of the clinical outcomes. We're even seeing a significant phase-dependent effect. And once we're unblinded, we'll be able to look at this a little bit more closely in terms of understanding if this effect is purely due to phase. And I should say, one thing that I'm very excited about is, even after we do this treatment, one of the things we do is we put the individuals back in the scanner and we rescan them. And so we're going to get now not just these are these models we have from the data before they got treatment, but we're going to get these after they have treatment. And I'm kind of like crossing my fingers, but one hypothesis is we're going to see one of these where the treatment worked. We're going to see one of these connections invert. It's going to become inhibitory. And that, I think, will be very exciting to show potentially how mechanistically this stimulation is affecting connectivity. So I'm just about out of time, so I'm just going to jump to the summary, which is, to say that this closed loop neurostimulation really offers us the possibility to improve efficacy of a treatment by timing the delivery of the stimulation to endogenous brain state. And this multimodal PhET system, that's really like perturbation-based neuroimaging, can be used to identify brain states that maximally engage a given therapeutic target. I think, if you go to NIMH, they want to, and you're looking at neuromodulation for a particular, treating a particular disease, it's always about like, all right, prove that you have target engagement, so of the therapeutic target. Future work, there's a lot of interesting stuff to do. So one is optimizing not just kind of the temporal targeting, but the spatial targeting. And so some of the spatial targeting right now is done through like neuronavigation and targeting a particular region of the brain based on a structural MRI. But what's also really interesting and links into this whole conference is the idea of the mind, the body brain connection. And so another kind of new result that has come out by a couple of groups is that it's clear that there's a circuit here that involves not just what's happening cortically, but also subcortically. For instance, engaging brainstem nuclei that are involved in regulating arousal and other types of neuromodulators, and that one could potentially use heart rate variability as a way to optimize the placement of the TMS coil. The idea being that heart rate variability is engaged differentially based on that sweet spot of the DLPFC that one hits, because now you're really aligned in terms of a circuit. And so, that's one thing that we're investigating, how to look at using body signals to spatially optimize and brain signals to temporally optimize the targeting. And then lastly, there's other neurostimulation modalities. Obviously, one is that I've been working on more recently is functional ultrasound with Elisa Canafagu here at Columbia. And there's some advantages of functional ultrasound in terms of this depth, but there's other issues in terms of really understanding how it works and what's the mechanism of action. So, you know, the nice thing about a closed loop system, it doesn't just have to be used to optimize something like the depth or the engagement of a region, but it could also be used to optimize certain parameters of the neurostimulation itself, even if the neurostimulation is in some sense unknown in terms of the mechanisms of action. So with that, just acknowledge all the collaborators, postdocs, also the funding organizations, and I'm happy to take any questions. Thanks.
Paul, was fantastic talk. We really appreciate, and I'm checking the chat box, and Robin, Arabian, Raut, I will
Hi,
unmute.
good afternoon.
Okay, please go ahead.
Thank you. Yeah, I'm a neophyte in this area, but I'm interested. My question is, you are mentioning about some circuits and things like that. So are there some proposed circuits which can emulate the EEG signals with certain pattern of input stimuli and things like that?
So if I understand correct, so you know, one of the things I show here just like a region of interest and how we engage that region of interest preferentially as a function of, let's say, the phase of the stimulation, right, relative to EEG. So when we look at circuits, at least at the macro scale, and we want to look at spatially distributed circuits, really fMRI is you know, the tool of choice. Now, what I can say is that, and something that's really exciting is that if we look at engagement, instead of looking at this region of interest that's the cingulate, but across the whole brain, we see different circuits engaged at different phases, right? And so, you know, we think that a lot of these, you know, a lot of these diseases and illnesses, they're circuit problems, and they're circuit problems at different scales, right? But for instance, as an example, what I didn't show is that if you look at the timing of the TMS relative to the EEG, and then you look at, let's say, the bold, you get very strong phase dependent activation in the posterior cingulate, right? Which is actually part of a big hub in the default mode network. So one of the things that we're doing as we're moving forward and taking this data, which is obviously still, you know, clinical trial, but we look at different ways to slice and dice it, is to look at network level properties and effects. And kind of, you know, another direction I want to take this has to do with even outside of questions, clinical questions. This in some sense can be, you know, new ways to understand cognition and cognitive neuroscience by allowing perturbation to be part of the imaging loop, and then to you know, actively dynamically sample by doing perturbation and making inferences on, you know, causal networks as a function of not just correlating things, but looking at correlations and then say, well, if that's really true, if I bang at this phase or at this location, I should see a change in network dynamics. So I think, you know, these kind of closed loop systems are important for our ability to really understand the cognitive neuroscience better.
Okay, Siri, you have the floor.
Thank you.
Thank you. Wow, Paul, I'm so impressed, not just with the work, but that how you can get this clinical trial actually up and going. So congratulations on that. Couple of questions. 30 minutes. How did you choose 30 minutes? Do you think 60 minutes every day would, lead to a more rapid plasticity and adaptation?
Yeah, great question. That's all based on what the clinical prescription is now, right? So it's true. There is the FDA recommendation and clinical care call for 30 minutes, I think, as a max. So and there are some issues. Like one thing that we also wanted to do was look at perhaps closing the loop in the scanner, right? So we could actually dynamically see changes. Turns out you can't, from a technology point of view, you can't do RTMS for too long in a scanner because of how things heat up and so forth. But so on the clinical trial, there are a lot of constraints that just have to do with, what the the current level of clinical care that's approved.
Yeah.
But I'm sure things like, another thing actually is we've tested this just with RTMS that's at this, that's 10 hertz or alpha frequency, right? But there's a lot of work in depression that are looking at these intermittent theta bursts. So they're kind of another type of stimulation paradigm. And the question, does that matter? We don't know yet, but once again, to demonstrate something clinically, we couldn't have too many arms of the study, particularly during COVID.
Okay.
And can I have a
Great.
quick follow-up? So yeah, in terms of you might have mentioned it, so I apologize if I missed it. Behavior, so related to Dr. Jimison's talk, right? So another metric to see what changes is as they're coming in every day over the weeks, how is their behavior working? Even just a simple step count, right? Are they moving more? Could be indicative of improvement. So, and did you ask them questions about daily living and things like that?
Yeah, great question. So, the Hamilton rating scale, and it's the Hamilton 21, they has some of that type of information captured. But then there's a whole bunch of additional, interviewing, survey, all that we capture, but just have not analyzed yet because everything's still blinded. But I totally agree that in one thing, I believe we were not allowed to videotape them. There was this discussion to see if we could do video, just even looking at changes in expression, right? Facial expression. But most of this is then captured through the classic, clinical battery that is the Hamilton and related survey.
Great.
Okay.
Thank you.
There are several questions came through the chat, and let me read them to you, Paul. One is, hope you can look at the ITPC at a follow-up visit to see if the effects are sustained and if they correlate with the symptom improvements. It's coming from Misra.
Exactly. Great question. Yes. So one of the things that we're excited about, right, is to see, all right, if there's an effect, what are some of these effects? Are they related? So for instance, do people that have greater entrainment, are they also the one that have the greater clinical effect? We've Zhao Sun, who I said had a poster before, she's also been looking at measures of excitability. And, so there are different ways to kind of look at the EEG data before and after to see differences and changes in excitability at different frequency bands that might be relevant. And so it could be that, there are effects that are predictive of clinical outcomes based on that. And what we're hoping, and this part of our analysis plan is, and anything in a trick in mental illness, particularly in depression, right, is that you apply the treatment and oftentimes it takes a week or 2 weeks, right, before we see any significant behavioral or clinical changes. But if we can start identifying biomarkers earlier on whether or not a given sequence or a given set of parameters is going to work, we can either decide to continue with them or we can optimize and change. So that I think is also one of the other ways in which we're looking at this, is as a way potentially to optimize treatment in terms of just time it takes to alleviate symptoms through these biomarkers.
Okay, Mahmoud asks, do you think these deep implanted devices can help in that depression remedy in near future? What limits, pros, cons you expect?
Right. So remember, this is completely non-invasive. So there's nothing implanted here. And so, there is this kind of spectrum of disease in terms of the severity of the disease where, there are some people where the disease is such that only an implant is really going to potentially have any effect. But there's, an implant requires neurosurgery. There's a lot of issues in terms of, you obviously have to get instrumentation put into your body. This non-invasive method can treat kind of a larger fraction of individuals who might not be willing to get an invasive implant. But then, we hope to be able to use these types of methodologies on clinical populations in the long term, right? And I think Shri asked this maybe in a previous talk, which is, if you could optimize some type of at-home treatment, right, using these types of methods.
Yeah.
Once again, you're not going to get a TMS system at home, but there might be other neuromodulation that this could actually have an impact. But that I think is more down the line. That's 10 years out or so.
Okay, I will unmute Michael Smith. Do you want me to read your question or do you want to talk, Mike?
Oh, first of all, I enjoyed your talk, Paul.
Okay.
Thanks, Mike.
Yeah, hi. Just a question. Interesting approach. Could it be combined with different type of brain stimulation for control chronic pain for patients?
Yeah, so that's a really good question. So I've been working a little bit with Elisa Canafago, who's looking at functional ultrasound for chronic pain. I have to admit, I know much less about pain than I do about depression. I don't even know that much about depression, but from what I understand, pain is really is very complicated, right? And so there are multiple different ways in which you can either block pain through looking at the peripheral nervous system versus trying to do things in the central nervous system. So, I mean, my guess is that there are this kind of framework of closed loop neurostimulation, we know is going to have lots of different applications. It might be, not closed loop neurostimulation of the central nervous system, but the peripheral nervous system, right? We know that there's, bioelectronic medicine or
Yes.
whatever the current buzzword is, is really focused quite a bit on that. So I do think that there are these other applications that probably include pain.
Okay. John, do you want me to unmute you, John Carmaker?
Yeah, thank
John.
you.
Yeah,
Thank
please
you
go
for
ahead.
for this presentation. I have a simple question. Did you interview your subjects, especially the control subjects, about how they liked the specific stimulations, and had they perceptions inside their brains caused by the stimulation? So the first one is, did you interview and ask how they liked it?
Yeah, so with the control subjects never got the full closed loop treatment because that is not prescribed unless you have major depressive disorder, but they did get the imaging in the scanner that included single pulse, TMS, the way that is dosed in the scanner is it's dosed at, so you kind of figure out. So you put TMS over the motor cortex, right? And you change the strength of it until they can move the finger in the contralateral atmosphere. Then you adjust that to about 120%. So it's like 20% above that threshold. And then they go in the scanner, and this is all done. The biggest thing is they just hear the clicking, right? They almost feel very little, because also the fact is that this part where we're actually stimulating is not close to any muscle, so they don't really perceive much of anything. So that it's really just they hear the clicks. In terms of the treatment group, yeah, that's a full clinical battery, right? So there's a clinician, a psychiatrist, they get interviewed, they get their Hamilton score. So all of that is being tracked just like they were getting any conventional treatment. Plus there's additional questions asked. So I can't say that since it's done at MUSC and we're kind of keeping data still kind of separated and blinded. I don't know all the details of, like kind of anecdotally what people thought. I can just, look at these Hamilton scores, and it's clear based on the Hamilton Clinical Index, they're all feeling better at the end, right? I mean, or not they're all, but clearly the vast majority is improving in terms of their clinical outcome.
Okay.
But you cannot say that from anecdotal that the patient stepped out of the room and said, that was a nice session.
Yeah, I don't know if they,
one.
Yeah,
No.
right.
Okay. Siri, you have a question?
Oh, yes, I just put in the chat. I just
I
wanted
know.
to know if, when do you get to find out which group is which, sync and non-sync?
We got about another month or two, I think.
Okay.
And we're already, guessing on certain things. Now, I will say there is one part of us. So it's a little bit, so there's two things I want to see. Well, one is obviously what the result is, and then what the final imaging looks like, right? So if I jump back to this, this little model here. So what we've been doing is trying to drive activity in the cingulate, right? And so we're actually, in some sense, driving this, whether directly or indirectly, right? And so the question is, should we be trying to drive this, or should we be trying to inhibit this, right? And there's, as we've gone through this trial, and because TMS, it's still unclear exactly the mechanism of action at the macro scale level, it's still possible that the groups could be flipped. We could actually be making things worse in the sense that non-optimizing it by, instead of inhibiting this to change this into a controllable feedback loop, we're actually making it less controllable. Now, I don't know that, I'm always trying to think about, all right, what's the different outcomes, and, if something is unequivocal, what could we use to, equivocate it or to clarify it? So I think a combination of how the network changed and how those change relate to which group they're in is basically going to give us a very strong hypothesis test one way or the other.
Okay. Misra, you have the,
Sure.
unmute yourself, please. Go ahead.
Yeah, thank you. And thank you, Paul, for the great talk. We do a lot of brain stimulation here at UCSD in treatment refractory depressed individuals, and my colleague, Dakshin Ramanathan, who's the clinician here who does the trials.
I'm sorry, Jyoti, we can't hear you. Can you
It's
crank
really
up
hard.
your
Yeah,
volume?
you're very
Actually,
faint.
I hear them. Okay, go ahead.
Actually, very faint. I can. Yeah.
Oh,
Okay.
Okay, I'll repeat myself.
I heard that you do a lot of work
With
there
deep
at
brain
UCSD.
stimulation.
Yeah.
Yes. So in this trial, I was wondering what two possible next steps, whether you plan to expand it to the more rapid approach of theta burst stimulation at all. And secondly, we've been thinking about having synergistic cognitive activity, and that would put oscillations in very specific evoked states that could then also be entrained, and what your thoughts about that were.
Yeah, I mean, two really great questions, I think. So, and it's one of these things, there's so many directions to go. It's almost, we're going to have to, as a team, try to figure out how to do this and what the, clearly, yes. So theta burst stimulation is one area where we think we should also go with this in terms of looking at optimizing closed loop. So I think, one thing is the open loop. So we can potentially, and kind of what's easy to do outside of a pure clinical trial is to look at kind of different types of stimulation in the scanner open loop and look to see how regions are preferentially activated or networks are preferentially engaged. So we want to do that. And I think we would do that obviously before running a clinical trial. The other thing is, and which I think is super interesting, right, is the context in which you deliver this, right? And so, we always think of, all right, the person is sitting there in their resting state, whatever that means. But is that the right thing to do? I mean, there's a lot of evidence, right, in that, at least for some of the neuromodulation methods that don't directly drive the brain, but maybe modulate, like TDCS, or that what might be critical is engaged in a task while the stimulation is delivered. So yeah, that's another definitely high on the list of kind of avenues to go with some of this.
Okay. Any other questions from platform party or through chat? I don't see any. Siri, do you see anything else? I think we covered all the questions and everything.
I raised my hand, Metin. Sorry, yes.
Okay, Gert, you're the
Yes.
last.
So first of all, Paul, I'd like to commend you on a really great talk. And from the number of questions, you can see this is really at the core this conference, right? You cover all the angles, and getting a closed loop biofeedback is really at the core of what we want for this non-invasive and very powerful therapeutics. A question about so you say this is well, definition non-invasive, whereas unobtrusive. So having an MRI machine around our head is not something that we can really afford, right? We can't really walk around with an MRI around us, right? But so EEG and even the I guess the coils is something that can be worn. So to what extent do you need the MRI? And the MRI was more used. The fMRI was more used towards calibrating and understanding the effect, right? So for the actual finding what the phase is, basically to couple your alpha activity with stimulation pulses, that's something that can be done without MRI, correct? And so then, so you can
that's what we do. Exactly. So that part, so exactly what you said, which is we calibrate, we identify the phase that maximally engages the therapeutic target. Then we have a different clinical system that's just EEG and TMS closed loop. And that, so, you know, it's absolutely correct. And I think, so I think the thing is, the fMRI then at the end allows us to kind of look to see how that engagement might have changed as a result of the therapeutics. But yeah, clearly it's not needed in the closed loop case. And I think one question is, you know, it's always, you know, being engineered. I mean, I'm an engineer, you know, by heart. And so when you think about how this would scale, right? And if you could do something like this in a broader population more cheaply, for instance, that allows us to engage in more naturalistic tasks. So we can really look at, all right, what's happening in my body, what's happening in the context of my environment, and when should I stimulate, right? Well, that's super exciting. And I think that there's, you know, the world of electronics and device development is going to get us to a place where we'll be able to make systems that are mobile, portable, non-invasive, that allow us to look at, you know, kind of the other side, which is we don't have, you know, quite as robust and sophisticated equipment, but we can put this stuff in naturalistic scenarios, and that naturalistic scenario itself might be so important to engage to having an effect being drawn out that, you know, that might be even more important than some big old fancy scanner.
Thank you.
If no other questions, it's almost 4:59. It's amazing. Look at the timing. Paul, never ever complain about my timing.
Yeah, I never do. Always on time.
And we started on time today.
I see another hand raised though, but
it took you 30 years, but Paul, I mean, we started on time, we are finishing on time. I'm sure Misha is smiling right now too, and as well as the group. Okay, this is a wonderful day. Siri and I, we really appreciate. First, these 3 exceptional talks, highly inspiring, not for you, Misha yet. Okay, and also the questions raised, wonderful questions, and the participation of our colleagues, and thank you so much. We really look forward to seeing you tomorrow. We start 8 a.m., right, Gert?
Yes, same time, 8 o'clock, yeah.
It's California time.
Yes.
Thank you, and enjoy the rest of your day. Depends on where you are, and look forward to seeing you tomorrow. Thank you so much. Bye.
Thank you.
Thank you.
Thank you. Bye. Okay, good to see you tomorrow.
See you.
Okay, thanks so
Thanks.
much. Have a good
Thanks,
night. Bye.
everyone.
Bye. Bye. Bye, Siri.